Greetings, chemistry students. Today we're going to talk about heat and a concept known as specific heat. For today's lesson, once we get into it, you're going to need a calculator and your chemistry reference tables. So if you need those, pause the video and go grab them. So first I'm going to run through a few key terms with you, some things that you should probably know, and then we'll dive right on into specific heat. So, first term is energy, and energy is the ability to cause change or to do work. So, things don't change. If you just walk over and you start like pushing against a wall and nothing changes, nothing moves, you haven't actually done any work. But in this class, we're mostly going to be talking about energy in terms of heating things up and cooling things down. The unit for energy is the joule, spelled Joule, not Juul, and it's abbreviated with the capital letter J. It was named after James Joule. Temperature is another thing that you may think you know what it is, but it's kind of hard to define if you're not a scientist. But scientists define it as the average kinetic energy of the particles of matter. In other words, it's essentially how fast are the particles moving. If you increase the temperature, particles move faster. You decrease it, they move slower. This then means there is a minimum temperature that you can get to, which would be when the molecules stop moving altogether. And that temperature is called absolute zero, which is negative 273 degrees Celsius, negative 459 degrees Fahrenheit, or 0 kelvins. Named after that temperature scale is named after Lord Kelvin, who discovered absolute zero. Thermal energy is the total energy in the particles of matter, both their potential energy and their kinetic energy. The potential energy part will become important when we talk about changing states, melting, freezing, boiling, condensing, that kind of stuff. And the last thing is heat, which is abbreviated, oddly enough, with the letter Q. Heat is the flow of thermal energy from higher to lower temperatures, and it's measured in joules. Because the thing we're going to look at in this class is, first of all, it's really hard to measure how much thermal energy something has, but we can very easily measure changes in it. We can measure how much heat moves from one place to another. And so this heat which moves is measured in joules. The Q stands for quantity of heat. If you forget that, it is on your reference tables. It'll tell you that Q stands for quantity of heat energy. And there's going to be a few formulas that use Q that are on your reference tables, and we're going to talk about the first one of those three formulas today. So to measure changes in heat, we're going to be using something called specific heat capacity, which is the amount of energy that's needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. So if you had 2 grams of a substance, it would require twice as much energy, or if you wanted to increase the temperature by 2 degrees, it would require twice as much energy. So there's a very simple mathematical formula that says Q equals M times Cp times triangle T, where Q is the quantity of heat, M is mass, Cp is the specific heat constant at a constant pressure, and that's what the little p means. It means the pressure stays the same. So the way you assume the pressure is the same is you leave whatever you're working with open to the atmosphere, and atmospheric pressure is relatively constant unless a tornado passes overhead in the middle of your lab experiment. So essentially, you just don't seal things up. We're not doing these experiments in a pressure cooker. That requires a whole different mathematical formula to work with. The amount of heat depends on the mass, it depends on this heat constant, and it depends on, this is the Greek letter delta, which means change in temperature. In other words, how much does the temperature change by? And the key thing about this is when you're heating a substance up, the kinetic energy is increasing as the molecules move faster, and so the temperature changes. And so this is just three things that are multiplied together that can tell you how much heat was added to the substance. Different substances have different specific heat constants. If you look on the front page of your reference tables for a whole bunch of different metals, you'll find different specific heat constants. For instance, aluminum has a specific heat of 0.897 joules per gram degree Celsius. So if you want to increase the temperature of 1 gram of aluminum by 1 degree Celsius, you need 0.897 joules. Gold has a specific heat of 0.129 joules per gram degree Celsius. So 1 gram of gold only needs 0.129 joules to increase its temperature by 1 gram. And then up here, there is also some specific heat constants for water. And for water, it depends on whether you're working with ice, whether you're working with steam, or with liquid water. But liquid water has a specific heat capacity of 4.18 joules per gram degree Celsius, which is one of the highest specific heats of any substance out there. That's why if you were to go to the beach this afternoon when it's supposed to be approaching 80 degrees, the sand at the beach will be nice and warm because sand has a fairly low specific heat. But the ocean is still going to be quite cold because the water takes a very long time for it to warm up. Water, for instance, if you put a metal pot on the stove that's empty and you turn the burner on high, it won't take but a few seconds before that burner is really hot. But if you have water in the pan on the stove, it's going to take forever for that water to heat up. But the pan itself will heat up really quickly because metal has a fairly low specific heat. Water has a very high specific heat. So now what we're going to do is we're going to look at some problems that we can solve. I'm going to show you this worksheet right here. Oh, hold on a second. This worksheet is called Specific Heat Problems. It's got 8 problems, and I'm going to work through 2 of them with you. All right. So I'm going to work through the first problem. It says, how many joules are needed to warm 25.5 grams of water from 14 degrees Celsius to 22.5 degrees Celsius? So the formula we're working with says Q equals MC delta T. And we're solving for joules. So Q equals, our mass is 25.5 grams. The specific heat constant for water, and between 0 and 100 degrees Celsius, water is a liquid. The specific heat constant is 4.18 joules per gram degree Celsius. And our change in temperature, if we go from 14 to 22.5 degrees Celsius, that is a change of 8.5 degrees Celsius. You don't have to worry about converting to kelvins, but if you felt like converting to kelvins, you got to be careful. You don't take this 8.5 and add 273 to it. You would have to add 273 to the 14 and 273 to the 22.5. And then when you subtract them, you'll get 8.5 again. So you only have to use kelvins for the gas laws. You don't have to use it for the specific heat problems. But now we just need to take our trusty calculator, and we'll take 25.5 times 4.18 times 8.5. And I'm coming up with the answer of 906 joules. And the reason we have these weird units is I'll show you how these cancel out. We had grams right there, which cancel with grams underneath. We had degrees Celsius and degrees Celsius. So we're left behind with a unit of joules. That's how problem number 1 works. And now I'm going to take you down to problem number 7. So let's see if I can move this out of the way. So for problem number 7, it says a sample of lead released 1.2 times 10 to the third joules when it cooled from 93 to 29.5 degrees Celsius. What is the mass? So our heat, Q, is 1.2 times 10 to the third. That equals our mass we don't know times the specific heat of lead. Well, if we look on our reference tables, the specific heat of lead, it's right there on the front page, is 0.129 joules per gram degree Celsius times, and if we go from 93 to 29.5, we take 93 minus 29.5. The difference between that is 63.5 degrees Celsius. So if we're solving for mass, then we need to take those two things and move it to the bottom. So in our calculator, we're going to take 1.2 times 10 to the third, which is also known as 1200. Then we're going to divide it by, in parentheses, 0.129 times 63.5. And I'm coming up with an answer. And the mass equals 146.5 grams. And by the way, this formula, the specific heat formula that's on your reference tables, it's affectionately known as Q equals MCAT, even though that's a delta or triangle, which means change in. I know it's not the letter A, but if that helps you remember the formula, there you go. But you can always use your reference tables. So what you need to do is go back into Google Classroom, and you're going to work on the other 6 problems on this worksheet. And then tomorrow, I'll introduce you to a couple more concepts with specific heat, and we'll move on from there. So good luck.